Good afternoon, everybody. So let us start our second week's first lecture. Today is October 24th, right? Okay, so just a quick recap. If you say go to the start here page, and you see that I have updated the syllabus as I discussed in our last lecture. So if you go to the content and see the syllabus, it is 2.0. So please download it and follow it. And there is a quiz. I uploaded a quiz based on this version of the syllabus. Okay. So the quiz is up now. Oh, I see 4 people have taken it. It will take, I guess, within 30 minutes. You can take it. But I have made it unlimited attempt so that you can take it and see full point. So in case if I want to give some bonus point, I will consider this one, okay, at the end of this semester. So better take it, okay, and then you will be familiar with our syllabus and policies, especially my communication policy. I'm very strict. If you do not follow my communication policy, I will not reply to your email. Okay, the restriction is that do not send me email from D12, right? The second thing is that do not forget to mention your course number and section. Let's say CS4306 W02, right? W2, then fine. I'm fine. Okay. Okay, that major change I have made, as I discussed in our last lecture, that I have assigned 5% points for your class attendance and class participation. Okay, so I'm trying to make a digital assigned attendance so that you do not need to take it. Maybe if I will try. If I get permission to use archive. Some of you use that, right? If you took 13, 21 or 22, we use archiver. Maybe I will do that. And from next week, whenever I select it, I will use this. But for today, let us do a manual attendance. Can anyone give me a page, please? This one should be fine. Okay. Yeah, one. Thank you so much. So this is okay, please give me a favor and then sign on the sheet. Write your full name and give a signature. Okay. So when you give a signature, please make it something like unique or something that is not be copied easily. Say for instance, don't do like something like this, okay? Okay. So there your assignment will be 20%. Okay, and then quizzes will be 25%, and then two tests will be 30%, and the final exam will be 20%, and then everything is same. Okay, there is nothing changed. Still I found a typo, spelling mistake. I will fix it, okay, without changing version. Okay, so this week we will start asymptotic notations of algorithm analysis. Okay. As we discussed in our last lecture, that today mainly I will go through the chapter 2, right? Chapter 2. Not chapter 3, maybe chapter 3. We went to chapter we went to chapter 2 in our last lecture, so we will go to chapter 3. Yes.
This is that program actually should have all the chapters listed out. You see that the symbols on the left, the one above the paperclip.
Here.
No, one down.
This one.
Yeah, that one. There
Oh.
you go. There's all the chapters.
Thank you for figuring it out. So chapter 3. That's it. Okay, I have PowerPoint slides. Okay, take the quiz, please. Quiz 0. Okay, and then our next quiz will be due next week. There is nothing due this week. Okay, so let me go through this and master theorem, and then I will have our quiz 1 mostly from this chapter 3, 1, 2, 3 and 4. Quiz 1. Okay, and then assignment 1 will be over there. Okay. Give me 1 second, please. Let me do what you have. Let me add it quickly. Oh, lecture videos and part. Oh, sorry, I forgot to add it here. Okay, I will add it later. Here, let me go through. I will add it here. So in our last, I will add this in the slide. So we discussed this in our last lecture. Okay, so let us start chapter 3. So chapter 3 is all about algorithm analysis in terms of asymptotic performance, asymptotic notation. That means we will consider either the upper bound, lower bound, and tight bounds in case of very large n. Okay, large number of n. So we literally will tell that these are infinite. So in case of infinite, we will check this infinite, but actually it is not infinite. So we say infinite, that means a very large number. We denote by infinite. Okay, so for instance, we will consider that a very large number. For instance, if I have a data like sorting algorithm, we will consider that this algorithm will be efficient for a large n. How large it is, that will depend on our data type, right? Every data type has its own capacity limit, right? So for instance, integer type has a limit, long has a limit, short has a limit, right? So in general, we will say this is a very large number. So in order to analyze algorithm, the common thing, that common notation we use is called big O notation. So big O means a capital O, uppercase O. Okay, so do you see this? Okay. Okay. So big O notation is the upper bound. You know that we say, for instance, insertion sort run in algorithm in big O n squared. That means if n become larger, so then its running time is n squared, because in the insertion sort algorithm we know that there is a loop, inner loop, right? There is inner loop and outer loop format. So one loop goes inside another loop, so we will have big O n squared, and we read this as big O n squared. So in general, the definition you will see in the book. I asked you to read the one page from the book. Okay, so we write, if there is a, for instance, do you see that here? We write fn is a function of another function. Okay, if is a function of another function, fn equal to big O another function, gn is another function. Okay, and then if we find a constant number c, that is a non-negative constant. Okay, c is greater than 0, and another n, maybe the is a natural number n is a positive number n. Okay, such that if we say that fn, okay, f of n for this n greater than this n is greater than this n0, if we find that fn is a positive number, but it is become less or equal to the constant number c times the value of gn, function value of gn. So for instance, if we have a function, we will come up with example later. Okay, but this is in general definition. Okay, so general definition that we know that a function is a relation, right, between two variables. Okay, some the variable of right side is called independent variable and the left side is called dependent variable, right? The variable of equal sign, the right side of the equal sign is called independent variable, and here in the left side is called dependent variable, right? So here on the right side, the independent variable is also another function, not a regular variable. So like the function is another function, gn. So gn is a function. For instance, here if you see that like this is the regular function fn, this is curving, the curving on fn. Okay, And if we find a constant number, has everybody signed on it? Okay, thank you. If we say constant number c is greater than 0, such that you see that at some point these two intersect, these two functions, that fn and c of gn, not only gn, the function value of gn multiplied by the constant, whatever the constant, if the constant we find, so that at some point it intersect, and then at some after that point the function fn never touches the c of gn. After this point it will never touch of gn. So the intersection point here, fn, okay, the intersection point here. So if we go like this way, this n is the horizontal axis, okay, and then at this point we say that n 0, okay, and in that case we say that this function is upper bound, okay. That means we say the running time of this function, we will say this is big O n, okay. So you see that it is positive, right? The right side, first quadrant, it is positive, okay. And fn at this point, after this point, fn is always down. It never passes, it never touches, it never crosses, okay. So if you understand this, remember this one, this is the big O notation. Then the omega notation, this lower bound is just opposite, okay. I like you to draw this a few times, okay. This curve is not necessarily will be like this, you can draw anyway, but the main requirement is that after this point n0, it will never, fn never will pass that way. So for instance here, if I if you want to draw something like this, if you want to draw on your free hand, so if you want to draw something like this, okay, and then if you this is c of gn, this is function, okay, and f of n okay. So here this is our, we have three intersection, okay, we have point 3 intersection. Here is one intersection, let me get a different color. Here listen, we have one intersection here, another intersection here, another intersection here. But the question is that where the n0 should be, this one, this point, or that point. So let us say this point A, and this point B, and this point C. So n0 will be the point at C, right? So at this point it never touches. So but here, so my drawing is that, you see that this drawing is not correct, right? It apparently seems that at some point it will touch, right? F1 has curving direction like this way, and C1 has, C of Gn has direction this way. It looks like that it will at some point it will intersect, right? So this is not a correct drawing for this one. You understand? Yes.
Just so I understand what you're saying, n0 is going to be the place where, like, the last spot that
last intersection.
The last one.
After that, there is no way that this fn function will touch or cross the c of gn function. You see that the difference between this one is correct, when why I say that my drawing is not correct. Do you understand this? Because it looks that it will be touching here somewhere, right? We don't know yet, but for safety, why don't you give this way? This way is correct. Okay. Okay, and another thing is that we got point A over here, B over here, C over here. Okay, apparently if we say that it will touch over here, right, it will touch over here, then maybe tracing or not crossing touch. Then if it comes like this way, then fine, then this one point will be C0. Okay, the last point of intersection, okay, is the point C. Okay, and then here, for instance, here C0 will be a C is a constant and n is this way, n is a natural number. So n0 it will be this type, this value. For instance, this maybe n can be 100 or 1000 or 599 or something, we don't know yet. Okay, has anyone any question about this? Okay. The way I think that if you understand what is wrong, right, then you will understand what is correct, right? Then you will not do the mistake. Okay. So in some book or some paper you will have this kind of different kind of definition, but same thing, same definition is there. Okay, this is the mathematical notation of that definition, and this is descriptive definition. In your book you will say definition, okay, you will see the definition, it has written definition, but the concept is that you see that this one and this one has same thing. Okay, like lower bound. Okay, if you understand the upper bound, then lower bound is different notation, or is opposite. Okay. Yes. Let me see if I have. Okay, so if you have a function, lower bound is defined as omega, okay, big omega. Okay, so then for insertion sort algorithm, running time is again omega n square. We will come back soon. Okay, why it is same for upper bound and lower bound. Okay, so here the function is mathematical formula is that omega of gn equal to fn if there exists a constant c that is greater than 0, positive constant, and another n0 that is a numerical number, positive number, okay, greater positive number, such that you see the opposite order, this one. So in the if I wish I could say that side by side. Okay, so here C of gn is less or equal to f of gn at certain point. Okay, so here you see that almost same diagram, but here you see that this is the n0 point over here. Okay, so this is the big O n and this is the small o n. So big O n, for the big O n we had this C of gn is the upper part. Okay, and here for the omega 1, if you see that at this point, let me check this one. At this point, this is the intersection, it's n0. Okay, and at this point Cn of gn, C of gn, it never touches Fn. That is, Fn is going up. It never touches over here. But in the previous definition, if you come up here, then you will see that one. Let me get that one. Okay, in the book we have two curves side by side, two. We are looking the B and C. We are looking B and C. Okay, not we are looking not looking the left side one yet. Okay. So let us recap the big O notation again first. So big O notation that at certain point, after certain point, it never, Fn never touches C of Gn, but in the omega notation is opposite. You see that you could write same thing, almost same drawing, same thing, but here Fn always pass at some point, it goes always upper. Okay, it surpluses at this point of Gn for the omega notation. Sometimes people mismatch. Okay, sometimes you will see say that one is big O notation, omega notation, maybe this one is big O notation. I like you to remember and understand one of these correctly. Okay, then you see that other thing, another one is opposite. Okay, now there is another notation, it's called tight bound, which is denoted by theta. Okay, f of n is a Gn. For instance, if after some time f of n lies between if there are two numbers C1 and C2, constant number, and after a certain value of n0, okay, and this function here is n0, so this function, this fn function lies in between C1 of Gn and C2 of Gn, and it never crosses either this or this. So they will this fn function will lie between C1 is a constant number, okay, and C2 is a constant number. So whenever we function, actually n is the value over here. So whenever we put the function n over here, we will get a value, right? For a function, we get a real number, maybe real value, and then whenever we multiply that by another real number, we'll get another real value. So at any point, this point or this point, whatever you say n, so this direction in n. So then here theta n will be lying in between. In other way, we see that if there is a common between omega and big O values, if there is a common value, then we denote that is for is theta notation. For instance, if an algorithm, it takes a certain time for both upper bound, the worst case and the best case. So this is the best case, okay, so the omega is the best case. Okay, so we have slide, we have book, and if you don't understand, do Google search, and maybe there are other resources available that you may like that explanation. Whatever explanation you like, I don't care, but you need to understand this. Has anyone any question about this? I like what you draw this. Take a piece of paper and draw this a few times. And then you will understand that how it they look like and then differ. Okay, the tight bound theta is called theta. If there is a common something, if n lies between C1 of Gn and C2 is Gn, and then there are two constant number. Okay. set. Oh, so it has like all in all we have here in 3 pages. I will upload these slides over there. Okay. So if we have a set of functions like this, the left one, okay, so then we say that, for instance, here we learned the last lecture, right? How do we find the big O notation? We will consider the dominant term over here, right, for large number. Here in this set, the dominant term is n squared. No matter it is 5, either this function or this function. Okay. Okay, and we know that it has n log n. N log n is always less, or at some point it's less or equal to n squared. So n squared is always dominant. So this is big O n squared. Okay, and here in this term, okay, this one in the middle. Okay, so we are looking for lower bound. So by looking this in terms of n, what is the lower bound? The minimum time it will take. Let us look for the minimum time it will take. For this one it will take n squared, right? And for this function it will take 3n squared. And for this function it will take n squared plus 9. So one thing that we will always here consider that the constant term. We will ignore the constant term. Okay. Here I see there is a mistake over here. Okay, so it has n squared. It should not be this one with linear n. It should be linear in something squared. So in my understanding there is a mistake over here. But where did they get it? And to see the explanation. So here it said that big O omega also n squared, and here so theta n squared will be the common one. So common one from this function set and this function set. If we take a union, okay, and then we will see that these are the common terms, right? These are the common terms, this function within these two functions. So then now, in order to find the tight bound, we will consider only this part, these three functions that are common. Okay, so this has a common part, right? So the common is 4n squared. So here n squared dominant term, here n squared dominant term, here n squared dominant term. So here tight bound will be theta of n squared. Okay. I'll see if I get the explanation of why they said 2n and 4n over here. Okay, so in the test or quizzes, you will be given some kind of this kind of function, right? So this is a function of fx. Fx is a function of x, right? And by looking this function, you understand and recall the concept. We can find this is big O value in 1 second. So big O notation is x squared, right? The dominant term is x squared, right? So for instance, the explanation, if you go through the explanation, at some point we will find a c value. For instance, here the c value will be 4. If you consider 4, okay, if you consider 4, the 4 times function of this is always less than or equal to 4 times x squared. So for instance, if any value, for instance 4 and or greater than 4, So think about if we have 4. So then this term will be 4 times 4, 16, right? And this term will be so at x equal to 4. So then fx will be x, so 4 squared plus 2 into 4 plus 1 equal to 16 plus 8, 24 plus 1, 25, right? Okay, and here this part c of f x squared will be 16 times c into 16. So then can we have a function, can we have a value of 6, that can we have this one a value c times 16? Can we get a real c value, positive c value? Like for instance, if c equal to 1, right? If c equal to 1, then we see that this times c equal to c 1 times 16, right? Oh, I'm sorry, this one will get c equal to 2, right? Then this time will be 2 times 16, 32, right? So then at this point, c for if c equal to 10, then we 25 less than 2 times 16. So here c equal to, so for c equal to 2, that is a positive number, right? For the definition we got c equal to 2, and n 0 equal to 4. Okay, it's satisfied, so that we say that this function has a upper bound of x squared. So at this point, so for this point, this function, the f of x, it does not touch the c of gn. Okay, let's go to the next one. How many slides do we have? So in the book there are some other examples like this. Okay, you will get some quizzes or assignments from the book, mainly from the book. Okay, you may not get exactly same questions, but you may get similar question. Okay, for this instance where I will be asking for this type, what is the c value? So it says for this one is here, c value equal to greater or equal to 4 and x greater than 7, then this function will have upper bound, and this will have upper bound of x. So without doing this calculation, so if we say that if a function is the dominant term, then just get rid of the constant term and then get rid of the coefficient, right? This is the coefficient, and then we have the term that x, then fx. Okay, then there is a formula that if a function has an upper bound of big O, then definitely it is upper bound is big O x squared. So for instance, if any function that is, so for instance, for this function, right, it has big O, it is upper bound with big O x, okay, then it is definitely, it will upper bound big O x squared, big O x cube, big O x to the power 4 and on any larger exponent value. Okay, that means if a function is big O, has upper bound big O x, then it is also big O x squared, then it is also big O x cube, and so on. Okay. Actually, this chart and this chart, it has some, in our last lecture maybe we did some kind of this calculation, right? So for instance, we say big O1, that means 1 is a literal number. You say big O1 or 10, whatever you say, if it is constant number, then we see it is value is 1. Okay, even big O5, big O10, and if it is constant number, then the result is 1. There is a 1 means a symbol, that is it takes 1 unit of time. Okay, and big O log n, if for instance here n is a value, so log, do you recall what did I discuss in our last lecture? Okay, so if we say log, then base 10, right? So log, this is base 10 of 1000 equal to log 10 to the power 10 to the power 3. Equal to 3. I believe here it will be LG. It will be LG, not log. It will be LG. Log is LG means 2. Okay, 2 to the of 1000 equal to LG 2 to the power 10, right? 2 to the power 10 equal to 1024, right? So it is approximately 1024. So it is approximate value is 10. It is approximately, there is a mistake over here. It should be LG, not LOG. Similarly here, because some books have mathematical, old book have mathematical location and notations LG. Okay, so here the interesting term is that if we have like this kind of function like 2 to the power n or factorial of n, but especially like this n to the power n, so then in case n become larger, this function takes a long time, right? Long time. So this value it raises, so this will take long time. So we will say that for the exponential function, okay, so we will try to avoid to develop any algorithm or to improve any algorithm that has like this kind of exponential running time. That are not good, right? For long time. it will take long time. Even factorial of n or even 2 to the power n. So in case it comes with a very large number. So this slide shows the for the n value, for the n. So which function is, you see the factorial n, it grows very faster, it goes very steep. Okay, and 2 to the power n like this way. And for instance, for this one, which one is better? In this set of functions, right? Which one is better, the best? The constant term, right? This one takes is, so after, if we ignore the constant term, then what is the next one? Log n, right? And then if you say n times here and n log n, it takes more time, and then n squared, it will take more time, and then 2 to the power n, it will take length. And which one is the worst algorithm here? In factorial, it takes, right? They did not give n to the power n. I think n to the power n would be the worst one. N to the power n. Did they give n to the power n? If they gave n to the power n, that could go like more steep. N to the power n could be 1, like 2 n to the power 1. It start with 1. So n to the power n. If n equal to 1, then 1 to the power 1 equal to 1 to the power 1 equal to 1, then it will start from here. If n equal to 2, then 2 to the power 2, it will go 4, right? Then n equal to 2, okay, 2, then it will be 4. If n equal to 3, then it will be 8. Sorry, I need to. So then this function, if n equal to, for instance, 100, for instance, n equal to 10 to the power 10, right? So then this function will be more steep like this. So n to the power n will go like this. My TA is knocking me. Give me a second. I need to turn on this notification. There are rules for symmetric and then transitivity. We don't need this relaxivity. We have a few minutes. Let us go through the next one. Okay. So the book have definition, right? So big O notation, and it has also a small O notation and then small omega notation. Okay, read this, all of this, and then you see that our next focus will be master theorem. There is a formula, standard formula, that is used for finding upper bound, lower bound, and then if what that exists, what does not exist. Okay, by looking, there is a formula. We will go through this formula. Okay, so that is called master theorem. We will go through this. So it has definition. You see that this is example. For instance, if you are given a function like this, okay, in your assignment or test, you will be asked to find the c value and n0 value. For which c value and n0 value, there exists an upper limit, upper bound. Okay, bigger notation. Okay. Let me go. The book has many examples. As I said, we will not cover everything from this book. Okay. Okay. So let us start today, and then in our next lecture we will go through this. We will cover this divide and conquer method. Mainly, in our last lecture we discussed that the merge sort algorithm uses divide and conquer method, right? So although it has, the algorithm name says divide and conquer, but it has three parts, right? Divide, okay, conquer, and combine. So the divide parts, what does it do? It splits, it divides the problem into some sub problems. Okay. So that each of the sub problems will be able to solve in a similar fashion. Okay. For instance, if you are given a set of data, you need to bring it to sort or merge. Okay. Then you need to come up with a smaller unit that you can do whatever you can do. For instance, 2 variables, 2 items, or 4 items, or 6 items, or 8 items, or larger items. Okay. So here the divide, conquer. Divide is split the problem, and conquer is the solve the problem recursively. Okay, each of the sub smaller unit problem, so that if the sub problems are small enough, and then it can be solved in straightforward way. Then the combined part, what it does, it combines the solution, okay, from all of the sub programs, then it will find the result of the original program. Okay. So here, so merge sort algorithm. So in general definition, or in the worst case, the Tn is the time it will be needed. So in mathematically, we can define that the merge sort algorithm has this time. This definition is in terms of the master theorem. We will learn that. Okay. Now, so the master theorem is said if n equal to a very small number, only one value or two values. Okay. Then we can sort it easily, right? If you have only one value, then nothing to sort. If you have only two value, right, then we can sort it by one swapping, right? But in case of large number, okay, so here this is the formula 2 of t, okay, n by 2, that is here n by 2, that is every time we are splitting our sort problem data set into half, so you are getting n by 2 data size is getting half, right? And then how many parts we have here? How many division? 2 divisions, right? So if one division subdivision takes this time, the total will take this time to solve. And also we need to have merging, right? So merging, it will take theta and constant time. Okay, so there here we will see that using master theorem we will get that it has theta of n log n time. We will get it theta and n log n time. Okay, there is a formula, it is called master theorem, and we will apply the master theorem to know this. Okay, and then this, like we saw that, I'm sorry, we saw that the insertion sort algorithm takes big of n squared times, right? And the merge sort no, I'm sorry, merge sort algorithm takes big O, or you can say theta, that is constant, in log, that means base 2 n. So which one is better, more efficient? Merge sort algorithm, this is more efficient, right? So for large n value, so this is less steep, this algorithm, this function goes less steep than that one, right? For instance, if we draw like this for very large algorithm, so then it will go n squared, will go like this way, and then in log base 2 n will go this way. This is that. So this is called master theorem. Tn equal to a of t is more total time equal to a of n by b, okay, plus fn. Here a is greater or equal to 1 and also b is greater than 1. So in case of our merge sort algorithm, what is the value of a and b? So b is here, how are we splitting our problem? Our problem is our data set is problem, right? Our given data set is our problem, that we need to merge it, sort it, right? Okay, the main problem is our data set, so we are splitting it, okay, by half. Okay, and how many times we are splitting? Every time how many pieces we are getting? 8 times, right? Here a will be 2 and then b will be also 2. Okay, let's go for this one. You see that this is called ceiling, this symbol is ceiling. Okay, for instance, ceiling of 9, if you say ceiling of, I'm sorry, ceiling value, for instance, you can say ceiling of 9.5, it will be 10. Okay, and then floor value, if you say AF 9.5 equal to 9.0. So this symbol is floor, okay, and that symbol is ceiling. This may happen, for instance, if you are given a data set of odd numbers n. For instance, if your data set, for instance, if you have n equal to any an odd number, right? So then, for instance, n equal to 9, easy, n equal to 9 or 11, whatever you say. So then you can split, one side will be 5 value, right, and another side will be 4 value, right? You cannot split exactly 4.5. We cannot give 4.5 elements one side and then 4.5 elements other side, right? Yes.
Is this function just for merge sort, or would you find
For any,
something like that
for any.
recursive?
Merge sort is an ideal example for divide and conquer method we are discussing. For any sorting, any algorithm that can be divided, any problem. We are considering that we are splitting our problem set, right? For the merge set algorithm, what is our problem? Data. I want to come up with some examples. This is the merge sort algorithm. What are the examples? Let me see, there are some good examples. Okay, here is the master theorem for solving our recurrences. We will focus on this one in our next lecture, but today I'm giving you just some heads up. For instance, over here, so for the master theorem for n is greater than 1, right? So we know that the formula is it takes a of t of n by b plus fn. So where n greater than 1 and b n greater or equal to 1, n can be 1, a greater or equal to 1, a can be 1 and b must be greater than 1, because we need to make at least 2 splits, right? Okay, but I have not actually seen any problem that n equal to a equal to 1. So if we have 2, b equal to 2 greater than 1, then definitely a will be at least 2. So still it does not make sense why we don't say n a greater or equal to 2. I would say a greater or equal to 2. Okay, let us see some examples we have here. So this is the master theorem, and okay, so this is important. You will get some test questions from here or assignment here like this. Okay, theorem 4.1, this is derived from the master theorem. Okay, this is the master theorem. If we have a greater or equal to 1 and b greater than 1, then let f be any function, then its Tn will be, okay, a of Tn by b plus Fn. Okay, so here n by b, as we said that it can be meant either floor or ceiling, or it is both. Okay, then here so then in that case Tn has the following 3 asymptotic bounds. Number 1, 2, 1, 2 and 3. You see that these two, number 2 is easy and it is tight bound. We say theta, tight bound, number 2. And this is upper bound. It is something less than here is a value is less than some with a epsilon value, and this one is upper bound. This one is upper bound, and this is lower bound is plus. So let us start with the middle one. Okay, so this is for tight bound. If we can write n in terms of a number like this, so for instance, whatever what we say that whatever we have value, right? For instance, here if we are given a formula like this, right? So then we know the value of b and a. If we know the value of a and b, right? So then we can plug in that value of b and a over here. Then we will get this part as a constant number. This part, this upper part, this part. So let me write it. It's a large font. Yeah, we're coming an example, right? Concrete example. You will understand that. If we go with the example, they will understand that. So for instance, this part, let me write it. If Fn equal to theta, I'm trying to write it. N is power, okay, to the power, I would say Lg log b and a. Okay, so this is n, and then this is log. We are considering that with base 2. Okay, so the Lg, this is like this one is like this one is like this, Lg 2 and a. Sorry, this is base b. This is b. Example, we can say if we have Lg 2 and then if we have 2, right? So this is 1, right? So in case, so we know that log Lg a base a of a equal to 1. So for any value, same value. So here for our merge sort algorithm, right? For our merge sort algorithm, we found that Tn equal to 2 T of n by 2 plus Fn, right? So here a equal to this value, this is a value, right? And a equal to 2 and b equal to this value 2, and then so if we plug in this a and b value over here, so here, then here if we plug in this, then theta of n to the power, okay, log 2 times log n, so equal to theta of, this is n to the power 1, this is 1, right? So theta of n to the power 1 times LGN, so then we can get theta of n log n. We have some past time, we have some examples in our last lecture. We will come, for instance, this one, okay? So here a equal to 9 and c equal to b equal to 3, right? And then fn equal to n. So in that case, if we plug in that formula, then we can find this is running time, and we will get T1 equal. And in the test or quizzes, you will have an expression something like this, but something like this, for instance here. So please spend some time. If you understand this, in our next lecture we will discuss this with some problem, okay?
Can you clarify what's being plugged into what?
We will discuss this in our next lecture, okay?
Okay.
Okay. So,
No, we didn't.